I'm going to solve a few more problems using average bound enthalpies. Then again, first thing I'm going to inspect is make sure my reactants and products are in gaseous phase, which is true in this case. Next, I make sure it's balanced. This is ethane plus hydrogen giving me ethane, so I need 2 more hydrogen. I put it there. Next, I'll do my Lewis-Dot structure to see if there is a double bond versus single and triple. In this case, there is one double bond here between carbons, which require more energy than a single bond. Hydrogen to hydrogen is always single sigma covalent. On the other side, you only have single bonds. This is saturated hydrocarbon. And then I'm going to just plug in my values, but before I do that, let's just see what bonds we are breaking. So I'm breaking 1 C2H, second one 3, 4 CHs. I'm also breaking 1 C2C double bond. I'm also breaking 2 hydrogens attached to each other, so 2 hydrogen single bonds. Minus, because products are exothermic, I'm breaking 1, 2, 3, 4, 5, 6 CHs, C to H. I'm also forming 1 C to C single bond. One other thing I like you to do is clean up and simplify if you can. It will help you with the next question that I'm about to do, but let's just look at this. If you have 4 C2H, on the other side you have 6 C2H, you can simplify this and say I'm only forming 2 in comparison. So 4 C2H goes away, I don't need that value. Let me go after C double bond C, which has C double bond C has the following value. It has 612 kilojoules plus 2 hydrogen to hydrogen, which is 436, minus, you only have 2 C2H because we simplified it to 2 C2H, and that value is right here, 412, 2 times 412, plus C to C single bond, which is 348. When we do the algebra, this delta H of reaction happens to be negative 287. Let me just write it one more time. Negative 287, of course, kilojoules per mole, exothermic because overall I'm negative. Bonds are stronger in products and more stable. The next question, problem number 3 that I want to look at is decomposition of hydrogen peroxide. Then again, you do Lewis-Dot structure. The equation is not balanced, so I need, on the other side, I need just 1 oxygen. I'm going to put a fraction, half of oxygen will do. Then let's do Lewis-Dot structure. Hydrogen peroxide has 2 lone pairs on each oxygen. Everything is single bond. On the product side, you have 1 H2O. And you have half oxygen. When you do Lewis-Dot structure, you realize it's a double bond. Now, let's just see what we are breaking. I'm breaking 2 OHs. I'm also breaking O to O single bond. Minus, on the product side, I'm forming 2 OH not right now, 2 O single bond H. I'm also forming half of an oxygen to oxygen double bond. Now, why did I say to cancel like terms on both sides if you can, or simplify? Because intentionally I covered up OH. If it's a multiple choice, we don't have to give you that value. We are hoping you realize that you can cancel them out. So eventually all you are doing is break 1 O to O single bond, and you form half of O to O double bond. And then it's easy, we just put it 146 kilojoules per mole minus half of 496. And when you do that, you get negative 102 kilojoules per mole. And that's your final answer using average bond enthalpies. The last problem for bond enthalpies I go after is sometimes you will also be challenged to actually bring the value of a bond enthalpy to life. In this case, they give me an equation, they give me the final delta H, and it's being asked what is the C to H attachment. If you look at this table, everything is given to you except C to H. That's a question mark. Okay, we can do it. It's simple algebra. Now let's see what bonds we are breaking. 1 C2H, 2, 3, 4 C2H. So delta H of reaction is sum of bonds broken. So for 4C single bond H, I'm also breaking a C to C double bond. The equation, of course, make sure it's balanced. It was balanced. I'm also breaking one hydrogen to hydrogen single bond. Minus on the product side, let's see what we are forming. You form 1, 2, 3, 4, 5, 6 C2H, and you are also forming one C to C single bond. Let's simplify as much as we can. The 4CH versus 6CH, this goes away. I only have to worry about 2 of them. Now I'm ready to plug in my numbers. Delta H of reaction is given to be minus 136 equals C to C double bond 612 kilojoules, H to H single bond 436 minus, don't forget 2CH, which we are trying to find the value for, plus 1 C to C, which is this, plus 348. When you do all the simplifications and your algebra, C to H, which you should calculate, should equal 418 kilojoules per mole for each one of them. So this is delta H bond enthalpy of C to H. Good luck.